So let's talk about CRISPR. So you've heard about CRISPR, you may not have a great sense of how it works. And for today's purposes, it's actually not that important how it works. I'm more interested in showing you what it can do. And so there are various types of CRISPR technology. I'm showing you two forms here. On the left is what you can think of as version 1.0, the original form. CRISPR can go through the whole genome, kind of like GPS, and find the exact place you want it to go, a target gene like PCSK9 or ANGPTL3. And once there, it cuts through the gene, and that cutting can lead to disruption and turning off of the gene. So you can kind of think of it as molecular scissors. On the right is a newer form of CRISPR technology called base editing. And this is actually more precise, more elegant in how it works compared to the original CRISPR. So here, again, it finds the target gene, but instead of cutting through it, it can actually replace one letter in the gene with another, kind of like a pencil and eraser. It erases a letter and then replaces it with another one. And so it actually has the precision to be able to change exactly one letter in the 3.2 billion letters in the human genome. That's the level of precision we're talking about. And so if you make the right letter change, you can actually turn off a gene as well. So both of these technologies will allow you to turn off genes. And just for fun, I want to show you what CRISPR looks like. So it really is a little molecular machine. Now, in the middle of this machine, you can see that there are blue and green strands. Those are actually DNA, and you can kind of see how they wind around each other, the DNA double helix. And then around the DNA is the CRISPR machinery. And so CRISPR actually can scan along a DNA molecule, scan entire chromosomes until it finds the target site, the target gene. And once it's there, other parts of the machinery then either cut through the gene like a scissors, or change a base, erase a letter, replace it with another letter. And so again, in the middle, you can see that PCSK9 protein levels were dropped by 90%, close to 100%, not quite there, but pretty close. And on the right, that resulted in almost 60% reduction in LDL cholesterol levels. Now, there are other medications that can reach that level of LDL reduction. Statins potentially can do it. PCSK9 antibodies can do it. But remember, all of them have short-term effects. They're medications you have to take again and again. So these are 2-week data. The question is, since the changes have been made in the DNA with the editing, will the effects last for a very long time, longer than the existing medications? And so last month, Verve gave an update, some of those same monkeys, but now followed for 6 months. And what you can see with PCSK9 protein in the blood on the left, with LDL on the right, after the drops at about 2 weeks, all the way out to 6 months, there is no hint whatsoever that the effect is going away. It is rock steady. And you look at data like these and you come away with the impression, wow, it's possible that these reductions will endure for the remainder of the lives of these monkeys. And so on the basis of these data, Verve has announced that they are hoping to be able to initiate first-in-human studies next year.